In this video, we are going to talk about the spectroscopy. So, spectroscopy is the study of interaction between matter and light. And in this video, specifically, we are going to talk about IR or infrared spectroscopy. But why do we care so much about the spectroscopy? So, spectroscopy is such an important part in organic chemistry because without it, we wouldn't be able to determine what we were making in organic reactions. So imagine that you are in the lab and you made a new compound, for example, a white powder, and you believe it can cure cancer. With spectroscopy, you can determine its structure within a minute. But 100 years ago, if somebody made a similar compound, it could take even years for scientists to confirm the structure of what they made in reaction. So spectroscopy drastically changed the way that we run reactions in organic chemistry. So the basic idea of a spectroscopy is that we shine light on our sample and then that is going to give us some sort of information about the compound. So all the spectroscopy techniques are going to deal with this electromagnetic spectrum that you can see here. And IR spectroscopy specifically is going to probe the infrared region of electromagnetic spectrum. So IR is going to tell us what kind of functional group present in our molecule. For example, if you make a compound and you don't know what that is, you can take an IR of your sample and recognize that, oh, you got a ketone or an alcohol or a carboxylic acid. So these are the information that we can get from IR spectroscopy. Now, if you think about molecules in 3D space, they are moving at all times. And that movement is happening through a variety of ways. So for example, we can have rotation in the molecules. We know that single bonds are rotating freely at all times. Or we can have vibration. And vibration is happening through stretching or bending in the bonds in variety of ways. Now, for each and every bond in a molecule, the energy gap between the vibrational states is dependent on the nature of that specific bond. Now, what does this mean? Now, we know that the energy of a molecule is quantized and a bond vibration is restricted to these energy levels. So, a bond can vibrate, for example, if it can absorb the energy that matches the energy difference between these two levels. Now, this energy difference, or what we call energy gap, is determined by nature of bond. So, for example, energy gap for CH bond is larger than CO bond. Now, IR spectroscopy can detect the difference in each bond's energy gap, and this allows us to determine what type of functional group are present in a molecule. So as I mentioned before, in IR spectroscopy, when we have different energy gaps, we are looking at different functional groups. For example, CH functional group is going to give us different peak than CO functional group in IR. So how does this happen? When you put your sample in IR spectrometer, a sample is irradiated with frequencies of IR radiation. And the frequencies that pass through, or basically the ones that are not absorbed by the sample, are detected by the instrument. We are not going to focus on the IR instrument in this course. As organic chemists, what we care about is the information that we can obtain from this instrument, which is the absorption spectrum. So here is the sample of absorption spectrum. Now, by the end of this chapter, you should be able to determine what are these peaks and what functional groups they are related to. The IR instrument measures the percent transmittance as a function of wave number. So we are going to have percent transmittance in the y-axis and wave number in the x-axis. Now, what does wave number and percent transmittance mean? So wave number equals frequency divided by speed of light, and it has the unit of inverse centimeter. Be careful not to confuse it with wavelength, which we show that with lambda, and it has the unit of centimeter. So be very careful of that. We always have a wave number in x-axis, as I mentioned, and we can get the spectrum usually from 400 to 4000 wave number. The region from 400 to 1500, we call that fingerprint region, and it's specific for each molecule, like human's fingerprint. But this region doesn't give us a lot of information. Almost all functional groups can absorb in this region. And if you look at the spectrum, there is a ton of peaks in this area, which is even hard to interpret. So we are just mainly focusing on above 1500, so the region from 1500 to 4000 in IR spectrum. Now, percent transmittance, which is in y-axis, is just how much light was absorbed by the sample. So the more light is absorbed, the stronger these peaks gonna be. There are three properties of IR spectrum that we need to focus on. The first one is wave number, that tells us where the signals are located. The second one is intensity, basically how intense is the peak, whether it's weak or strong. And the third one is the shape, whether we have narrow peak or a broad peak, such as this one. Now, all of these features tell us about the functional group that we are looking at in specific molecules. The first characteristic is wave number, that tells us where the peak is located. So there is an equation that we need to talk about. You don't have to calculate wave number using this equation. This equation basically relates the wave number with force constant and reduced mass in harmonious oscillator. But what we actually care about in this equation is the last two bullet points. So the wave number is inversely proportional to the mass. You can calculate the reduced mass using this formula. So imagine that we are thinking about vibration between these two atoms, and each atom has m1 and m2 mass. So you can simply calculate the reduced mass using this formula, and the wave number is inversely proportional to this mass. So what this is saying is that some atoms with higher mass are going to have lower wave numbers. And also wave number is related to force constant, which is related to bond strength. So it is directly proportional to the bond strength, meaning that the stronger the bond between two atoms, the higher the force constant and the higher the wave number would be. So for example, we know carbon-carbon triple bond is stronger than carbon-carbon double bond. So in IR spectrum, carbon-carbon triple bond appears at higher wave number comparing to carbon-carbon double bond. So as I mentioned, wave number is dependent on two factors. Now let's look at a few examples here. So the first factor was mass. So the smaller the atoms or the lighter the atoms, vibration is happening at higher wave numbers because mass is inversely proportional to wave number. Now here we have a bond between carbon and different atoms. So carbon-hydrogen bond vibrates at 3000. Now if we replace hydrogen with deuterium, which is heavier than hydrogen because it has one proton and one neutron, we are going to see the vibration reduces. So it's going to vibrate at 2200. Now the basically heavier the atoms get, we are going to see reduction in the wave number. Now the second factor is bond strength. So bond strength is directly proportional to wave number. Basically, the stronger the bond, the higher the frequency or the wave number would be. So let's look at the bond between carbon-nitrogen. We have carbon-nitrogen triple bond, double bond, and single bond here. So carbon-nitrogen triple bond is stronger. Therefore, we are going to see that vibrates at 2200, which is higher than carbon-nitrogen double bond and carbon-nitrogen single bond. So we say that hybridization can also influence the wave number. To explain this, we are going to look at a CH bond connected in alkane and alkyne. So the CH bond in alkane usually appears at around 2800 to 3000, and here is the general shape for that. We can also show it as sp3H, meaning that this hydrogen is connected to the sp3 hybridized carbon. Now the CH bond connected in alkene usually appears at around 3000 to 3100, and here is the shape for it. So CsP2H. And the CH bond connected to alkyne usually appears at around 3300. So as we move from alkane to alkyne, the CH bond vibrates at higher wave number. Now, why is that? So we know that sp orbital resembles s orbital more than sp2 and sp3 hybridization, and also sp orbital is closest to nucleus comparing to sp2 and sp3. Therefore, the CH bond in alkyne will be shorter and also stronger comparing to CH bond in alkene and alkanes. Therefore, we are going to see that CH bond connected to alkyne vibrates at higher wave numbers. So a very important point here is that we are looking at CH bonds connected to single, double, and triple bonds here. We are not looking at CC double bond or CC triple bond, so they appear at completely different frequencies. We see CC double bond at 1600 to 1700, and CC triple bond at around 2100 to 2200. Also, tetrasubstituted double bonds or internal triple bonds, they don't have any CH bonds, so we cannot see the CH vibration at 3100 or 3300 for these type of structures. Resonance can also influence the wave number. So if you look at the ketone, CO double bond usually appears at around 1720. Now if you have a conjugated ketone, so this ketone is conjugated because we have a double bond, single bond, double bond. So two pi bonds are separated with a single bond. So in a conjugated ketone, we see that CO double bond vibrates at lower wave number. So what is the reason behind this? Now to find the reason, we need to look at the resonance structure for ketone and a conjugated ketone. So for the ketone, we can draw a resonance structure by pushing the pi electrons over oxygen. Now in this structure, the CO bond is a double bond, but in this one, the CO bond is a single bond. That means the carbonyl group has some double bond and some single bond character at the same time. But the double bond character is more significant because in this resonance structure, carbon is positively charged and it's not octet, and also we formed formal charges which is not favored. So this resonance structure contributes a small amount in the overall resonance hybrid. Therefore, the CO bond in ketone has mostly a double bond character and it vibrates at around 1720 wave number. Now, if we have a conjugated ketone, we can draw three resonance structures for that. In two of them, the CO bond is a single bond, and in the first one, we have a CO double bond. So again here, these two structures are not significant because in both of them we have positively charged carbon and we form formal charges which is not favored. Now if we compare the conjugated ketone with ketone, In conjugated ketone, the CO bond has more single bond character due to presence of this one additional resonance structure comparing to CO bond in the ketone. Therefore, vibration of this bond requires lower energy, and we are going to see that appear at lower wave number. Signals in IR spectrum can also have different intensity. We can have weak signals or strong signal. Now, what can affect the strength of signals in IR spectrum? So the strength of signal is dependent on the dipole moment. So when bonds are stretching, their dipole moments oscillate. So if we have a stronger dipole, we see a stronger signal in IR spectrum. Now if you look at CO double bond, we know that oxygen is more electronegative than carbon, so it pulls the electron density towards itself. So we are going to see a very large dipole moment in CO double bond. Now if you look at the CC double bond, so here we have two hydrogens attached, here we have two alkyl groups attached. So these alkyl groups may pull the electron density down a little bit, but this causes a very small dipole in this molecule. So you can see the difference in oscillations for CO double bond and CC double bond. This can also appear in IR spectrum. So CO double bond usually shows a very strong signal in IR spectrum. However, CC double bond has very weak signal in IR. So the stronger or the larger the dipole moment, we are going to see more intense IR signal. Signals in IR spectrum can also be very broad or very narrow or sharp, and this is really has to do with hydrogen bonding. So we see that alcohols and carboxylic acids functional groups usually give us a broad signal in IR spectrum. So this is the spectrum for an alcohol. The OH functional group usually appears at around 33 to 3400, and it's always a broad signal. So this is due to the effect that we call weakening effect. Alcohol molecules are making hydrogen bonding in the solution. So once again, hydrogen bonding is an intermolecular force, so it's happening between the molecules of alcohols in the solution. And here is the hydrogen bonding between these two molecules. So just pay attention that this hydrogen bonding is different from the actual covalent bonding between this oxygen and hydrogen in a single alcohol molecule. Now in IR, we care about the strength and vibration of this covalent bond. So whenever OH forms a hydrogen bond, this interaction weakens the covalent bond between oxygen and hydrogen in alcohol molecule, and this makes the OH signal to be very broad. So basically what we can say is that the hydrogen bonding and this weakening effect are the reasoning for broadness of signal in IR spectroscopy. So carboxylic acids show similar behavior only in more pronounced way, because molecules of carboxylic acid can form two hydrogen bonding interactions. So they are going to form a dimer, and double the hydrogen bonding is happening here. Therefore, we are going to see even more of a broader signal in carboxylic acid. So whenever you have a carboxylic acid, it's going to take significant portion of your signal, maybe from 2200 to almost 3600. Now, one thing with carboxylic acid is that you always see a carbonyl group here at around 1700. And here, due to hydrogen bonding, even the CO peak is broadened. The last significant peak is amine, so we can tell the difference between primary and secondary amine. A primary amine is a nitrogen or amine attached to one carbon or one alkyl group. So here we will always have two hydrogens attached to nitrogen. Now, if we have a primary amine, that primary amine can have two different types of stretchings. Those hydrogens can stretch the same way, we call that symmetric stretching, or they can stretch in opposite ways, we call that asymmetric stretching. So due to these types of stretchings, two different peaks can appear in IR. So the primary amine is completely different from alcohols or carboxylic acids, but it shows up close to the same region. It's about 3500 here. Now with secondary amine, nitrogen is connected to two carbons or two alkyl groups, and we only have one hydrogen connected to nitrogen. So we only see one type of stretching. And with the secondary amine, we'll see only one peak, again in the same region at around 3500. So this slide is basically another way to recall the shapes of the functional groups that we just talked about. So they say that alcohol is more like a smooth tongue, which is funny. And carboxylic acid can be like a hairy beard, maybe. We can have vampire fangs for primary amine, or something like knockout fang for secondary amine. So when I saw these pictures, they sound very interesting to me, so I thought that maybe I can bring them to you. Hopefully they can be helpful to remember the shape of the peaks that we just talked about. So this slide is talking about table 14.2, which summarizes key signals in IR. So this table is very important. You should be able to know these numbers not by memorizing them, but by doing lots of practice problems. So you should be able to know where the carboxylic acid appears, where you can find carbonyl peak, or where you can find CC triple bond or CC double bond peak. So you should be able to recognize these functional groups in IR. Now tomorrow we are going to work on some practice problems related to IR, and we are going to use these numbers and this table to work through those practice problems.